got a good alternation, and everything looks good.
Until now, the European Space Agency's contribution to spaceflight has centered upon unmanned space vehicles. It was European science, and it is many months before the final assembly is ready to be placed in the payload bay of the Columbia. Once this is completed, Columbia and Spacelab are coupled to the external tank and the solid rocket boosters for their journey into space.
Redundant set sequencer start, T-minus 20 seconds and counting. The SRB nozzles have been moved to start position. Coming up on 10, T-minus 10, 9. We have go for main engine start. We have main engine start. Minus 3, 2, 1.
After the launch from Cape Canaveral, the two solid rocket boosters burn out and separate. They are jettisoned into the Atlantic Ocean for recovery and reuse.
Columbia now performing an evasive maneuver, moving below and beyond the external tank.
On board the orbiter, the crew monitor trajectory information, and the orbital maneuvering system inserts Columbia into a pre-planned low orbit, some 260 kilometers above the surface of the Earth. The payload bay doors slowly open, and Spacelab's first mission begins.
She's been deployed, working great. We have done all the way through.
This flight will last for 10 days. The crew members crawl through the access tunnel that connects the orbiter with the manned Spacelab module.
Orbiter unloaded on page 1-13. Okay, we've got the power on, and we're getting ready to turn it on.
Okay, sounds good.
A thermal shield, which blankets critical structures, provides essential protection from the extremes of temperature that are experienced as the orbiter circles the Earth every 90 minutes. On its first Spacelab mission, the Columbia carries a crew of 6, 2 pilots, 2 mission specialists, and 2 payload specialists, including the European scientist Dr. Ulf Merbold, and the American scientist, Dr. Byron Lichtenberg.
Okay, I understand.
Merbold and his European and American colleagues have undergone a long period of training for the Spacelab program. They must be familiar with every piece of equipment and each experimental procedure, for once in orbit, the success of the mission depends upon their skills.
In Houston PLT, we have completed the procedure.
The experiments are diverse, ranging from the study of containerless liquids to investigations of the response of the vestibular system in microgravity.
Sounds like you're ready to start the independent.
Inside the pressurized module, the scientific program is activated. The crew work to a rigorous schedule that has been prepared over several years. Much of this vital information is relayed to Earth as it becomes available. This is transmitted from the orbiter to ground-based data receiving stations, either directly or via the tracking and data relay satellite system. Data is collected and will eventually be distributed from the Goddard Space Flight Center in the United States. Spacelab has been designed to become an international research facility, available to scientists and commercial users drawn from all over the world. From the payload operations and control center, scientists on Earth can communicate with the Spacelab crew by voice and closed-circuit television links. This access to the European-made space laboratory allows them to monitor the progress of experiments and to intervene by either instructing the crew verbally or by sending automated commands to the onboard computers.
A lot of teleprinter messages that have come up over the night. The one we'd like you to look at first is 35 Alpha.
After completion of its first 10-day mission, Spacelab and the Columbia prepare for the re-entry maneuver. As the orbiter is drawn by the gravitational field of the Earth, it re-enters the atmosphere at an equivalent ground speed of nearly 27,000 kilometers per hour. Protected during re-entry by its shield of thermal tiles, the Columbia makes its final approach to the runway at Edwards Air Force.
In the summer of 1966, Esro launched 8 rockets here. 7 of the payloads were prepared at STEC in Holland, backed by research groups in West Germany, Great Britain, Belgium, and Italy. During trials here in 1965, luminous vapors of barium and trimethyl aluminium were released at a height of 120 miles. Some newspapers and radio stations were soon reporting mysterious heavenly phenomena and flying saucers. Esro does not have its own base in Greece either, but a center was built in Greece in May 1966 to study the solar eclipse. Radar and telemetry equipment monitored the Arcus and Centaur rockets, which were launched at that time. Here a Centaur rocket is being made ready. It's the same type that is used at S-Range at Kiruna. The Esro personnel we see here did not have much use for their light summer clothing when they arrived some months later in wintry Kiruna. This temporary yet solid design shows that the Greek base was not intended to be permanent. Between 1964 and 1966, Esro launched 30 rockets from outside bases, on Sardinia, in France, Norway, and here in Greece. A Centaur rocket, which we'll soon see launched into space, is built especially for studying the upper atmosphere. It is 20 feet long and weighs half a ton. It carries a payload of from 66 to 140 pounds. A Centaur reaches an altitude of about 90 miles and is aloft 6 or 7 minutes.
The motors are loaded into the launcher using this drawbridge, which contains part of one of the 3 launching rails, and when raised forms part of the launcher structure. The first things to go to the launcher are the motors. The larger one is the Raven, the main propulsion motor. The Cuckoo booster is the smaller one, painted red. Together, these motors are capable of sending Skylark payloads to heights of about 250 kilometers, depending on the weight. In the case of S-26, the planned maximum altitude is 190 kilometers. From the transporter, the motors are slid onto the drawbridge. First the Cuckoo, then the Raven. Fins have previously been fitted to the motors to stabilize the rocket in flight. The adapter bay between the motors enables the Cuckoo, when burnt out, to fall away 4 seconds after launch. The drawbridge is hoisted into a vertical position to locate the motors in the rails ready to receive the payload. Now a trailer known as a grasshopper brings the payload to the foot of the tower. The grasshopper rotates the payload to a vertical position. The BAC assembly team will now couple the payload to the motors. They will connect the umbilical cables and perform such last-minute tasks as fitting the flight batteries and aerials and removing covers. We now go to Titania, only 20 kilometers from Perles-de-Fogu as the crow flies. Before the campaign started, some special equipment was sent out to Titania from UK. Here in this shed, Dr. Hall of RSRS has set up radio transmitting equipment which will send signals to his receivers in the rocket. Titania was charged.
RS transmitters on.
15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, feu.
Skylark S-26-2 was launched successfully at 14:32 hours local time on the 27th of September 1967. Good telemetry signals were received for 6 minutes 51 seconds and recorded satisfactorily. All event pulses occurred correctly and all deployment systems worked as planned. Data was successfully obtained from all experiments. All information is recorded on tape and taken to ESDAC, Esro's data center at Darmstadt in Germany.
Flight pressure.
101 years after Hubble's birth, NASA and ESA will launch an orbiting
Coming up on the 1
2.4
minute
meter
point
optical
in our
space
countdown,
telescope,
everything going smoothly.
appropriately named the Hubble Space
And the
Telescope.
ignition of the solid rocket boosters and liftoff. Liftoff of America's space shuttle, and the space shuttle has cleared the tower. Houston now controlling the control
Orbital maneuver starting. 20 seconds left. Good.
In terms of size, the Hubble Space Telescope is not particularly large. It is smaller than many ground-based observatories like the William Herschel Telescope in the Canary Islands. But although this telescope is large, sophisticated, and 2,600 meters above sea level, it still has to peer through the Earth's atmosphere to see the universe. This is a typical observation of a star. The seeing effect, as astronomers call it, is distortion caused by the passage of the star's light through the turbulent layers of the atmosphere. This effect can be seen with the naked eye. In space, stars do not twinkle. For all these limitations, a first-rate ground-based observatory is still the equivalent of reading a newspaper headline from a distance of 1 kilometer. With the Hubble Space Telescope, it will be possible to read the fine print as well. Good, but not enough. Placing an optical telescope above the Earth's atmosphere radically changes the possibilities for astronomers in 3 fundamental ways. First, it removes atmospheric impedances, and in principle at least, this promises a 10-fold increase in image quality. Observations, for example, of the planet Saturn by the Hubble Space Telescope should be on a par with some of the spectacular images recorded by Voyager in 1979. Distant galaxies, which are at present just a blur through the best Earth-based observatory. After launch, the shuttle enters an orbit 296 kilometers above the Earth. The shuttle is designed to place spacecraft into orbit around the Earth, and so cannot send Ulysses on its journey to Jupiter. To do this, an upper stage consisting of an inertial upper stage, or IUS, and a second rocket called a Payload Assist Module, or PAM, are used. Gently, the entire assembly is elevated out of the shuttle's payload bay. When it is angled at 58 degrees, a spring release system pushes it away from the shuttle. The shuttle now backs off, its mission completed. Ulysses and its upper stage are on their own. The IUS contains its own navigation system, which now has to get Ulysses into the right orientation to begin its journey to Jupiter, whilst at the same time protecting its precious spacecraft. It turns tail towards the sun and starts to roll the whole assembly slowly so as not to overheat Ulysses. When the IUS computers have decided that the rocket is correctly oriented for the start of the interplanetary voyage to Jupiter, the rolling is stopped, and the first of its two motors are ignited. Ulysses surges away from the Earth, picking up speed until the first stage is burnt out. Coasting for a short while, and then igniting the second stage. The IUS computers check the velocity and orientation, and when they are satisfied, the second stage is discarded. The PAM now takes over. First, it spins Ulysses to 70 revolutions per minute to increase its inherent stability. It then discards the spin motor assembly and fires a Star 48 motor to gain sufficient energy to reach Jupiter and swing around the planet. After burnout of the Star 48, it has to de-spin Ulysses to 7 revolutions per minute. As an ice skater extends her arms to slow down, so the PAM throws out weights on the ends of lines. These absorb energy and slow the spacecraft to 7 revolutions per minute. The PAM is then discarded, automatically switching on spacecraft radio transmitters to NASA's Deep Space Network tracking stations. Ulysses is en route to Jupiter. Well, almost. Through the Deep Space Network, ESA's team members now have control and take steps to protect Ulysses thermally by making sure that it is spinning approximately at right angles to the Sun. They also make small corrections to the original injection orbit, which may not have placed it with complete accuracy on course to Jupiter. One by one, the Ulysses payload of scientific instruments are switched on, and a radio boom containing gamma ray and magnetic sensors is deployed, together with an axial and 2 wire booms. Some 50 days after its launch, Ulysses has become what it was designed to be. A fully operational scientific research instrument collecting data all the time as it travels through space. Jupiter is one of the most majestic planets in the solar system. It is also the largest. In its atmosphere, a huge 300-year-old storm rages, whilst smaller cyclonic regions of turbulence create the exquisite bands of color that characterize the giant planet. It is 318 times the size of the Earth, orbited by 16 moons, and is about 778 million kilometers from the Sun. It has a very strong magnetic field and is surrounded by formidable belts of radiation. But one of its oddest features is the speed of its rotation. Jupiter turns once every 10 hours, and this extraordinary speed is probably a factor in determining the strength of its magnetic field. To provide more data on these effects, Ulysses will make detailed measurements of the magnetosphere of Jupiter as it flies by. 485 days after its launch, Ulysses begins its entry into the Jovian system. It is traveling in a trajectory 30 degrees north of Jupiter's equator. Some 12 hours after it begins its entry, the gravitational grip of Jupiter tightens on the tiny ESA spacecraft. Ulysses begins its southern descent, sweeping across the darkened equator at a distance of about 450,000 kilometers. As it passes the southern pole of Jupiter, Ulysses has begun its long journey towards its end objective. Gradually, the great planet fades into the distance as Ulysses speeds out of the ecliptic plane and into the uncharted regions of the heliosphere. This is what scientists have been waiting for.
But what exactly is their interest in the Sun? To begin with, Ulysses will use Jupiter and the Sun to conduct a curious experiment. As it leaves Jupiter, the spacecraft will come into a position in relation to the Sun at which background noise is minimal. It will use this opportunity to search for elusive gravitational waves. Theoretically, it may be possible to detect these by measuring minute radio perturbations.
Although not a primary part of the Ulysses mission, the discovery of gravitational waves would be a breakthrough for physics. They should exist, largely because the Ulysses mission is the corona of the Sun. The Sun's external regions are divided into a photosphere, a chromosphere, and finally the corona.
It radiates outwards in vast streamers, forming curious plumes around the equatorial zones. From time to time, coronal holes appear at the open polar zones.
On other occasions, loops form which are associated with solar flares, but these appear to be confined to the Sun's equator. The loops set up local magnetic fields or closed loops. The corona consists of plasma or ionized gases with temperatures about 1 million degrees Kelvin. This itself is odd. The temperature of the photosphere beneath the corona is much probable, or there is a heat generation and heat flow mechanism between the two that is not understood at present. The complicated, erratic and highly energetic structure of the corona produces the solar wind, a stream of plasma flowing through the solar system. The solar wind can be easily observed in high northern or southern latitudes of the Earth as it becomes trapped by the Earth's magnetic field. The result is a spectacular display known as the aurora borealis. But the solar wind is also very chaotic. Although it radiates outwards, its flow is not constant. There are storms and gales, periods of comparative calm and quiet. Finally, the Sun acts like an enormous dynamo. Its external regions rotate every 27 days, whilst its internal layers rotate more quickly.
This generates a magnetic field, but the field itself bursts.
Now, if we can imagine all these solar features assembled together in a computer model, Ulysses' view of the Sun would look something like this. In June 1994, 4 years after launch, it will approach the southern polar zone of the Sun. It will cross this zone over a period of 5 months. By February 1995, it will cross the ecliptic plane and the equatorial zone of the Sun. By June 1995, it will then begin its passage across the northern polar zone, completing this by the end of September. Even by that stage, our view of the Sun may well have changed quite fundamentally.